Okay, so I've taken on perhaps too much material today, so let me get started. First, though, just an announcement. There's an update to Homework 7. I guess there's a revision and I think a hint for Problem 2. So please go to the web page and check it out. And what I'm going to do today is to talk about two closely related topics dealing with hashing. And hashing is something I'm sure all of you have seen before, but it's a very important topic. And we're going to talk about a couple of aspects that I think most of you won't have seen before. And though I'll comment that there's also lots of other things about hashing that would be good to do as well, okay, which we won't get to. So maybe just as an initial reminder that the basic idea of hashing is that you typically have a set of keys, which I'll denote capital S. And these keys come from some universe that I'll call U. So U is the possible keys that you might be storing. So in particular, what you might think of U being as maybe Social Security numbers. Okay, so these are 9-digit numbers. So in principle, then, for this case, there would be perhaps 10 to the 9th of them. Okay? But the number you're actually storing is typically much smaller. So for example, if you were storing Social Security numbers for students at Davis, you might be storing 40 or 50,000 such. Okay? So typically, the size of your set S of actual keys is much, much smaller than the size of your possible set of keys. And let me say that what I'm going to be talking about first comes from section 13.6 in the text. And in that, one of the examples that they give is where people are storing news articles. And as a new news article comes in, you want to see if it matches one you've already stored. Okay? And in this case, for the news article setting, they use as their key the first 100 characters. Okay. So you take the first 100 characters of the news article and you use that as a key, and you at least hope that if two news articles have the same first 100 characters, they're the same. Okay. And in that setting, the number of different keys, okay, so your universe U is all 100-character strings. So this might be something like 64 raised to the 100th power different possible strings, if you assume there were something like 64 common characters in your set, upper and lowercase letters, digits, and maybe a few other things. Okay, so this is a vast number. Right? The number of articles you're actually going to store is much less than this. Okay, so that's an important thing to keep in mind. Right? And then the basic way, of course, that hashing works is that we have a table where we're storing items. Okay? Typically, it'll be convenient to number it from 0 to n minus 1. So for our purposes, n will be the table size. And we'll use a hash function h. So this is our hash function. And it maps key x to some value in the range 0 to n minus 1, okay, where here x is some element of this universal set that we've described. Okay. So for example, if h of x is 10, then at least ideally, we'd like to store key x in location 10 of the table. And then later, if we want to look it up, we know that the place where x should be is location 10. Right, so at any rate, this should not be particularly novel. Okay, just bringing everyone up to speed. Okay. All right. Well, what's the complication with hashing in the setting we have? We have a set U of possible keys that gets mapped to a table that's much smaller than this set of possible keys. Yeah, collisions. Please use the mic also. Yeah, you're doing it. Yeah. So we know that because the table size is much smaller than U, this H is not a one-to-one function. It's in fact a many-to-one function. So in particular, because of the way we've set it up, for any hash function h, okay, there are going to be many keys x and y where h of x equals h of y. Okay. So whatever hash function you pick, there are some sets of keys that will perform very poorly. Okay. And that complicates analyzing hashing. And probably many of you have seen things in your prior courses that gave some sort of argument that hashing performs well in an expected sense. Okay? And most of those arguments are, let me say, a little bit flawed in their assumptions. So we're going to deal with this by taking a somewhat different approach. So what we're going to do here is deal with a topic that's called universal hash functions. And the idea of this is to kind of turn the normal hashing scheme that you think of on its head. So normally you think of that you pick a hash function, and then you have a set of keys that you're storing in your table, and you hope that the hash function works well. Okay? What we're going to think of is that you have the set of keys, and then we're going to pick a hash function from a collection of possible functions. And we're going to have the property that if we pick a random hash function from this collection, then it will work well on average. Okay, so this universal hash function, again, means that we're going to have some collection of functions. So think of this script h as having a bunch of functions. So h1 and h2 and h3 and so on. And in fact, we're going to have typically a pretty huge set of possible hash functions to choose from. Okay? And we're going to be able to prove things of the form, if I pick a hash function randomly from this collection, it's going to work well for any initial set. Okay? So now the game is going to be the following. So let's put it in here. Step one is you have a known set S. Well, sorry. Known is actually a bad term. Let me say fixed. Okay. So you don't actually know it. Somebody else has fixed it for you. You don't even get to see it. Okay. You have a fixed set of keys, say, of size m. Okay. And step two is you pick a random hash function h from this collection capital H. Okay? And this hash function is going to have the property that H maps your universal set into this range 0 to n minus 1. And as long as the number of keys you hash isn't too big compared to the table size. Okay, so in particular, that if m is equal to or less than n, okay, so you're hashing no more keys than your table size is, then intuitively it's going to work well. And I'm going to define that works well more formally in just a moment.
Is n fixed for all h in big H?
So is m fixed for all h in big H? Okay, so that's a good question. And in fact, m is not fixed, but n is. And in fact, when we talk about it a little more formally, we'll refer to these collections, say, as H sub n, where this will be a collection that's mapping keys to a table of size n. Okay? Now, actually, we'll actually want a different parameter as well. Anyone think, what else might I want to know about my collection? So n is saying when I map a key, it's being mapped into this size value. Okay? But what else does a function usually need to know? So this is the range, if you will. The range says I'm mapping it into values of this. Sorry, couldn't hear?
Sorry, the load factor. Load factor?
Load factor. The load factor, yeah, has to do with the ratio of m and n. But that's actually not going to, you're right that that's an important property, but it's actually not going to factor directly into H itself. It's going to determine how well H performs. Okay.
We might want to only inspect a certain number of bits of the domain.
Okay, so you might want to only expect a certain number of bits, but in fact, we'd ideally like to use all the bits of the domain. So in fact, this value capital N, which I'll remind you is the size of our universe. Okay, so this is going to sort of determine how long are the keys that you're hashing. So the hash function is going to be determined by the number of bits in the value you're hashing and by the final value that you're going to hash it into. Okay. So this is kind of the intuitive preliminary. And the specific things that we want is the following. Okay, so let's move over here. Okay, so we want our collection, we say that our collection of hash functions, script h, should have three properties. And this is described in 13.22 in the text. And the first one has to do with this fact that it performs well. Okay. For any two keys, u and v, in your universe U, okay, so again, this is going back a little bit to what I said before. Start with two fixed keys. Choose a random H from your collection. Okay. Then the probability that these two collide is equal to or less than 1 over n. Okay. And again, let me emphasize that here we're assuming that our universal collection is mapping to a range of size n. So that's where this little n comes from. Okay, so this is giving you sort of the effect that people assume in simpler analyses of hashing, that it's as if you mapped u and v to random elements of the table. Okay, so if instead of a function, you just picked a random position in the table, if you picked two random positions in a table of size n, you only have a 1 in n chance that they'll hit the same place. Okay, but this is saying that for a real function h, it has that property. Okay, so it's not just an assumption. You can actually prove this about certain collections of hash functions. Okay, that's true for any pair. Okay, for any two keys, if you choose one of the hash functions at random, the collision probability for those two is at most 1 over n. You have a question, Victor? Yeah. Well, it's the same for all pairs in U and V. Notice, let me say, it's not an independence thing. It doesn't tell you that if you know that U and V don't collide, what that tells you about another pair x and y. Okay? In fact, for some pairs, you would know something. If I told you U and V don't collide, you might know that x and y also don't collide. Okay, so that it's not as strong as that. So let me comment that it gives you this property that's the same as picking random places in the table. It doesn't give you all the properties that just picking random locations would give you. It's not as strong as that. Okay? It specifically says this. It doesn't say more. Okay? And the second thing that we'd like to have is that we can describe these function h compactly. Okay, for the schemes to be useful, you not only have this nice collision property, but you can, in some ways, describe. You could imagine that if the program that computed h was very complicated, and if each one was very different from the other, that it wouldn't be as easy to deal with. Okay? And somewhat related to that, what's a third kind of property that you might want to have for your hash functions?
Fast.
Yeah, fast to compute. Okay. Okay. And the key thing is that there are collections of hash functions that give you all three of these properties. And such ones that have all this can be called a universal collection of hash functions. And let me comment that in the original definitions, possibly only one. Okay, one talks about what it achieves. Okay, but to have it be useful, you'd like to have all three. Okay. And let me just briefly talk about how you do this. The book gives an actual collection of it. It describes it a little bit more formally of how you can achieve this. Okay. And I'm going to give you the idea, but I'm not going to show that you achieve property 1. Okay. I think it'll be reasonably obvious that 2 and 3 are achieved by this. Okay. So the hash functions that I should comment, there are several such collections that satisfy this. Okay, I'm going to stick with the one in the text. So in the one in the text, what we associate with each h in this h and n. Okay, so remember, n is the size of the table you're using. Capital N is the size of the universe you're drawing keys from. Okay. Right. So for an h like this, they can really just be described by, so this vector, this particular h is described by a vector of constants. So a1, a2, sorry, I think that the, up through a sub r, okay, where these a sub i's are values in the range 0 to little n minus 1. Okay, and maybe let me just comment one other thing. It's convenient for this to choose a table size that's a prime. Okay, you get the properties you want. And what you can think of is that typically you have an ideal table size in mind, and you can pick a prime that's close to that. Okay, and that will work. Okay. But that's really just a technical requirement. Okay, so we have these R values in the range 0 to n minus 1. And the hash function, which we can call h sub a1 through ar. Okay, so the hash function is described just by these R constants. Okay, so these are constants. And if we apply this hash function to a key x, it's simply the following. You break x into a bunch of blocks. So think of that x, your key is b0, b1, up through bi, and the number of bits in here is just log n. Okay, so take the first, so remember n is your table size, take the first log n bits of your key, and let's call this x1. Okay, and then you have the next actually, sorry, this is I plus 1 bits, and I guess this is I plus 1 bits again. Okay, so this is again log n bits, and this number is taken as x2, okay, and however many bits there are. Okay. So you can, how many bits are there in x, by the way? Remember back to that? Yeah, log of big N. Okay, so we go out to here, and finally it's b sub k, where this is just log of capital N. Okay, so remember that the whole key depends on your universe size. You break it up into these blocks, and then the hash function is just the summation I equals 1 to r xi times ai, and the whole thing taken mod your table size. So this gives you a number, taking it mod n, puts it in the 0 to n minus 1 range. So it's a straightforward thing to do, right? You've got your key, you break it up into these R pieces, and you then do this multiplication and modding. Okay. And I'll maybe just comment that R is log capital N over log little n. Since this is the number of bits in your whole thing, and you're breaking it up into blocks of this size. At any rate, the main thing I want you to notice is just that this is a relatively simple kind of thing to compute. Okay? And what the collection, okay, so what this collection H consists of is a different hash function for every vector. Okay? Each vector gives you a different hash function. So really picking H from the whole collection is equivalent to picking A1 through AR. So if you pick the coefficients in this, that gives you your hash function. So anyway, all this is in the book. And the book proves, going to here, that you actually get property 1 using this scheme. Yeah? Why is the block size log n? The block size is log n to make the proof that you get property 1 work. And I'm afraid, since I'm not going to go into that detail here, if you look at what they do in the book, it'll give you at least some insight into that. Okay.
If we're going to inspect all log big N bits of,
So you're looking at the whole key.
then, but log big N is also the maximum time we would spend by using a balanced binary search tree. So why bother with hash tables?
OK, so one of the things you're saying, OK, so if you're going to look at all of it, right, so I guess I'd say there's a couple of things there. Part of it has to do with what are the costs of the basic operation. In a balanced binary search tree, there are, yes, well, in a balanced binary search tree, the number of operations is actually log of little n, right? The number of items that are actually in the tree. Each of those operations, though, is a comparison of 2 log capital N bit numbers. So in a sense, the binary search tree takes work, right, this times log capital N, at least if you're going to compare all the bits in the keys in your search tree. Now, how that compares to these multiplies, depends a little bit on what hardware you have. In practice, typically these blocks are small enough so that this is a unit hardware operation. Okay. While comparing 2 log capital N bit numbers typically is not. Those keys are too big, or at least maybe too big to fit in. It's, I don't know, it's not a simple question to answer, but usually this will be actually faster. But yeah, there are some, in fact, information theoretic limits that say you can't beat a certain number of operations, but it's sensitive to a lot of assumptions. OK, so this is really part 1, and that's in the book. Part 2 is an application of universal hash functions that's not in the book. Okay. So what I'm now going to talk about is perfect hashing. And this is in a book that some of you may have, or at least have seen. This is in the algorithms book by Corman, Leiserson, Revest, and Stein, and it's in section 11.5 of that. This is the second edition. Just curious, how many people have that or have seen it? Okay, so anyway, I'm going to try and do this in a little bit more detail. So we're now going to look at something a bit different, which is now saying, suppose that we now actually have a known set of n keys, which I'll call capital S. Okay, so this is different than before, where we wanted to have something that would work for any set. Now we're assuming that somebody tells us this is the set of n keys that you want to actually store. Okay? And this comes up in settings where, say, you have an online encyclopedia or something like that that's kind of fixed, at least for a long period of time. Or it also comes up if you have a set of machine instructions. Okay, so you have some known fixed set of things that you're going to want to look up. Right? And what we're going to show is how to find actually a hashing scheme. And we'll see why I'll call it a hashing scheme. So we can look up any key in S in order 1 worst case time. Okay, no more averages. So I can look up anything in this one in constant time. Okay? And also, I'm going to do this using only, actually, theta n space. Okay, we'll see that it's actually easy to do this if you allowed yourself more space. Okay. People clear on what we're going to try and do? And I'll say that the perfect hashing in one sense means hashing with no collisions. And we're going to use that as a subpart of our overall solution. So let me do this in sort of 2 parts. So let me talk about the building block first and sort of the real perfect hashing scheme, which is that if I have n keys and I hash them into a table of size n squared. Okay. So I'm going to use a big table. Okay. Then in this case, I can get fairly easily collision-free hash functions. So in particular, suppose that I pick a hash function h from a collection that gives me n squared, okay, of these size table. And we're not going to really worry much about the size of the universe. Okay, the universe is kind of fixed, and what we're mostly going to be focusing on here is the range. Okay, so this really influences the cost of an individual hash computation, but we're going to mostly focus here on the table size. Okay. So what I'm going to ask now is, if this is the case, if I do this, what's the probability that I can hash my n keys with no collision? Okay, so that's what I want. And I'll claim that this probability is equal to or less than the probability that the following are true. Okay? The probability that key 1 in my set, So let me do the reverse thing. So this is what we want is no collision. So what's the probability that there's equal to or greater than 1 collision? Well, if there's equal to or greater than 1 collision, either the probability either key 1 and key 2 must collide, or key 1 and key 3 must collide, so on for all pairs. Sorry, for each of these collide. Okay, so I've picked my particular hash function h, and there's a probability that each of these pairs of keys collide. Now let me comment that this is an overestimate, okay, because this includes the probability that multiple keys collide. Okay, so there are some things where, like 3 keys collide, but the probability that at least 1 collide is at least this. But what are these terms? Okay, what did we say? If this is a universal collection, what was our basic property about what the probability that 2 given keys collide is? Okay. 1 over the table size. Okay. So each of these is at most 1 over n squared. And how many terms are there in this summation? N minus 1? No, actually, maybe the way I wrote it might have been a little bit. I heard n minus 1 and n squared. The answer is, as often, somewhere in between. Yeah, n choose 2, the number of distinct pairs of keys. Okay, so there's a term in here for each pair. So this is, this expression here is equal to 1 over n squared times n choose 2. And n choose 2 is just n times n minus 1 over 2, which we can upper bound by n squared over 2. So this is less than n squared cancels this, and we get an over 2. So it's less than a half. So when I pick a random function from this universal class, the probability that I'll get 1 or more collisions is less than a half. So that means that if I want to find a collision-free hash function for a fixed set of n keys, what I can do is say, OK, I've got my n keys. I'll pick a random h. Okay, so let me actually write this out. Okay, so we fix n keys, pick a random h, and let me not worry about the universe size. So just we're mapping to a table of size n squared. Okay. And if h works, that is no collision, then we're done. We found a collision-free hash function. And we just said this happens at least half the time. Half the time, if you pick a random one, it works. Okay? And suppose it doesn't work. What can we do? Yeah, try again. Okay? If not, go back to here. And since you have a 50-50 chance or more of succeeding each time, you'll pretty quickly find one that works. All right. Okay. So if we have a big table, easy to find a collision-free hash function. So what else? What remains to be done then? Remember, the goal was you've got a fixed set of n keys. You want to store them in a way that you can look them up in worst case constant time. Okay, so I went through, I found an H that works. I've now got something with no collisions. Okay, but I wanted something else. Yeah, linear space. And this is n squared space. Not so good. And a comment, even today we got lots of space, but with caches and things like that, smaller space is still good. Right. So to beat this down, what we're going to use is a two-phase approach. Okay. So we have our set S, and let me now name these as x1, x2, up through xn. Okay, so we have our n keys. Okay. And what I'm going to do is to use, as I said, a two-phase approach. So I'm going to use first a hash function h to partition S. Okay. So what you can think of is that let's create a size n table. So we have our usual thing, right? It goes from 0, here actually let me do it here, 0 to n minus 1. And let me now let S of I be the set of all xj's such that h of xj is I. Okay, so there are certain keys that map to there. So let me just give you an example. Suppose S is 6, 12, 14, 17, and 23. Okay. And let me use a really simple hash function where h of x is x mod 6. So I'm doing this just for simplicity of illustration. Okay. So 6 and 12 both map to 0. 14 maps to 2. 7 and 23 map to 5. So what I have then is that S0 is 6 and 12. S1 is empty, as is S2. I'm sorry, S2 is 14. S3 and S4 are both empty also. And S5 is 17 and 23. OK, so this is not collision-free, right? Got collisions here, here. Right? But what I'm going to do then is to use a second hash function for each of these sets that has more than one element, that has a collision. Okay, so step one is use H to partition. And then what I'm going to have intuitively, and let me redo this up here, is that I have my table, and here now it goes from 0, 1, 2, 3, 4, 5. Yeah. And so what I'll have here is a hash table for the items that hash to 0. So this table will store 6 and 12. And because there are 2 items, I'll use a table that's the square of this little set size. Okay, so this table will be, say, of size 4. And maybe to put this a little bit more precisely, I have this partitioning, and let's let n sub I be the size of my set S sub I. Okay, so the number of items that collide at location I is n sub I. Okay. And what I'm going to use then is a table of size n sub I squared. Now we just said if I want to store these items in a table whose size is the square of the set size, it's easy to find a collision-free hash function. Okay? So what I'll store here is not any items, but actually the hash function h0. So what is h0? h0 is the collision-free hash function for this set. Okay? So let me just state that h sub I is a collision-free hash function for S sub I. And this is taken from a universal collection H n sub I squared. Okay, so the size of the table I'm going to use for S sub I is the square of the number of elements in that set. Okay. And again, if you want to be complete, we still have the same universe size. The key length is still coming from this. Okay. And similarly, well, for 1, you can mark something that says, well, S1 really doesn't have anything. You can have a special thing that says it's empty. For S2, we'd have actually only 1. You can actually just store the key value if you want, presumably with some flag that says there was no collision. And for S3 and 4, you'd have that. And for S5, you'd have a table, again, of size 4 for 17 and 23. Okay. And again, this one, H5, okay, is also taken from ones that are going to 4. Okay. Now, by the way, if you really remember back, these tables wouldn't actually be of size 4. Okay, why not? It was a long time ago. Okay. What are our what did I say we wanted our table sizes to be? They need to be primes. 4 is generally not a prime, so we'd actually probably use size 5. Okay. It's OK for this to be a little bigger than n sub I squared. Okay. I hope it's intuitive that if you change the table size from 4 to 5, that does not increase your collision probability. Okay, so now I hope it's reasonably clear how you do a lookup. Okay, so if you want to find a key x, step one is to compute h of x, which is some element I in this table. Okay. So you go there. If you get, say, one of these null ones, what does that tell you? Okay, the key does not exist. It's not in your set S. If you get this, it tells you this is the key that's supposed to be there. If it matches x, yes, x is in the table. If not, it's not in the table because nothing else collides here. Okay. However, if you were looking up, say, 6, you have to do it in 2 steps. Okay. So to find 6, you'd compute first h of 6 is 0. You go to the table and you see, I need to do another lookup. You go to this table and you compute h0 of 6, which, say, was 3, just for example. And here in location 3, well, sorry, probably here, still probably numbered from 0. Okay. At this point, you would find it. Okay. All right. So, and at this point, either you find it, or if it's not there, it's not in your set. Okay. So in the worst case, 2 hashes. Okay. Worst case, 1 hash with h and 1 hash with the function you found here. And let me just remind you, can we go over to this screen just for a minute, that the compact description is important for achieving the linear space. Because we couldn't describe the function here going back. If I couldn't describe h0 and h5 simply, then that would be an extra space overhead. Okay, so it's a pretty simple scheme to do. Okay? You have your initial one that partitions it. For each of the subsets, you then find a perfect hash function by using its table of the square. Okay. And there's only one last thing that I didn't quite justify. And I'm not going to have time to do all of it. But the last thing is that for order n space, you need that the summation of the n sub I squares. Remember, for each subset, we need a table that's the square of its size. Okay. We actually can get this so that it's equal to or less than, say, 4n. Okay, this is not a requirement. You need this to only be order n, but in fact, you can get this down to 4n pretty easily. Okay. And the way you do this is you pick h, and if the summation of the n sub i's is too big, in this case greater than 4n, then try a new h. And again, because you're picking from a universal collection, you can say, see if this h divides them fairly evenly. If it does, the sum of the squares is small. If not, try again. And I'm sorry I ran out of time, but you can show fairly easily that the expected value of the sum of the n sub I squares is less than 2n, in fact. So what you end up sort of doing is using, going back to here, something like order n space for the initial table, something like 2n space for the secondary tables. So it's pretty space efficient. Okay, so we're only slightly over time. So, and anyone came late, do notice the Homework 7 revision